It's actually there on the YouTube channel, the first Lala live video. So can I start? All right. So hi everyone. Welcome to Online Study for You. In today's video, we are basically going to discuss a couple of very important topics with respect to TCS NQT. So the first topic that I'm going to discuss will be on binary search. So I'll be solving some questions on modified binary search, and then I'll be also be solving a question on stacks and queues, so that you actually get to understand how the thinking behind stacks works, how stacks actually work, and how on looking at a question you can understand, if we need to implement stacks in this particular question or not. But fine. So let's start with the first question. So the first question that I've picked up for today is, it's a lead code medium problem. It's known as search in a rotated sorted array, right? So yeah, you guys can read the question. So it says that we have a rotated sorted array, and we simply need to find an element in this rotated sorted array. Now, if you read the question, initially, norms array was sorted in the ascending order, right? And it has distinct values, right? Now, after that, I have rotated this norms array at an unknown pivot, okay, such that the resulting array has been rotated. So, okay, what does this mean? Let's try to understand this first. Okay, I think I should take this example. Let's come here. Let's take a different color and okay. So this is an example of a rotated sorted array. So if you look at this, particular array, this array has some special features, right? So this is not a sorted array. So if you consider this array as a whole, this array is not sorted anymore because it has been rotated. But if you cut this array into two halves from here, right? This part of the array is individually sorted, and this part of the array is also individually sorted. So can you somehow try to make use of this particular observation, that the array is sorted by the halfway mark, or the array is sorted across some pivot, right? For here, the pivot is this point. So everything on the left is sorted, everything on the right is also sorted. So the question here simply says that we are given a rotated sorted array of this kind, which I just told. And I simply need to find whether a particular element is present in this sorted array or not. Like if you look at this example, here it asks if 0 is present, or if 0 is found in this particular rotated sorted array or not. If it is found, then we have to return the index. So in this case, 0 is found at index number 0, 1, 2, 3, 4. So in this case, my answer will be 4, okay? In this case, my index of target, which I need to find out, is 4. But if a target is not found in this array, so if the element is not present in this array, in that case, my answer will be -1, right? So if it is not found, then you simply return -1, all right? So that is the question. Now, so this array is a rotated sorted array, right? But had this been a normal sorted array, then we already know how to solve this question, because that is what the normal binary search algorithm, the simple binary search algorithm states, that given an array, if my array is sorted and I need to find an element in my sorted array, I can find it in O of log n time complexity, right? So here also you need to write an algorithm. If you look at the last line here in the question, you need to write an algorithm with O of log n runtime complexity. This essentially means that you also need to implement binary search here in this particular question also. But the only catch here is the array is not sorted as a whole here. It's a rotated sorted array. So the question essentially states, or the question essentially comes down to the point that how will you modify the binary search such that you can actually implement a very similar algorithm in finding out whether that target element is present in this array or not? So this would be very similar to a normal binary search, but with some extra conditions. All right. So let's try implementing this. So I'll just try to copy this here. I'll try to implement the normal binary search over here as well. Okay. So, okay. So how do we start our normal binary search? We have 2 pointers. You remember? We have something called a low pointer here. By the definition of binary search, I should write it like this. Just take a low pointer here, and you just take another pointer here, which is the high pointer. Low pointer always remains in the first index. High pointer always remains in the last index of my array in a binary search. And how do we find out the mid in a binary search? It's very simple. We just do low plus high by 2, where low and high are the indexes. So in this case, the index of 4 is 0. What is the index of 2? It is 0, 1, 2, 3, 4, 5, and 6. So it is 6 by 2, low plus high by 2. So in this case, my mid is at an index number 3. So here is my mid. So this is my mid. Okay. What I need to do is I need to break this array over here through my mid, and then I need to check whether my left half is sorted or my right half is sorted. Okay. For example, if you look at this particular array right now, this left half is sorted. This 4, 5, 6, 7 is actually sorted. However, if you consider this as a whole, 7, 0, 1, 2, this is not sorted because 7 is coming before 2, which doesn't make it sorted in the ascending order, right? But 4, 5, 6, 7 is sorted. So what you need to check here is that which half is sorted. Okay, so your first step here will be just find out which half of the array is sorted. Okay, that would be your first step. How do you find out that which half of the array is sorted? We start from the left half. We first check that if the left half is sorted or not. Okay. How do we simply check that? It's a very simple if condition. You simply check. So the array is known as array ARR. Okay. So you simply check that if ARR of low is less than or equal to, it can also be equal, is less than or equal to ARR of mid. In case, my array only has one element. In that case, it will be equal. But okay, in this case, you simply check if ARR of low is less than or equal to ARR of mid. That essentially means what? That essentially means left half of my array is sorted. Okay, left half is sorted. So if you look at this example, 4, 5, 6, 7 is the left half, and my left half is sorted. Okay. So once you recognize which half of the array is sorted, then you can further go down on that. Okay. So inside the if condition, you can further go down. If my left half is sorted, you can actually check that if my target element, which is 0 in this case, it's better we write this down again. So my target element is 0. So if my left half is sorted, I will check again if 0 is at all present in my left half or not. Okay. First, we check if the left half is sorted or not. If it is sorted, then I will check if 0 is present in that left half or not. Because I need to shift my search space to the point, or I need to shift my search space accordingly where 0 is present. Because our ultimate goal is what? Our ultimate goal is finding where 0 is. Like, give me the index where 0 is. So here I will simply check if 0 is present in the left half or not. How do I check that? Again, it's very simple. You just check that if ARR of low, you just check if 0 is present somewhere in the middle or not. So you can just check that if ARR of low is less than equal to target, and target is less than equal to ARR of mid. So this simply means if target is present somewhere in between my low and mid, which simply means if target is present in my left half or not. Okay. If target is present in my left half, then you do what? Then you shift your search space onto your left half, because what is your aim? Your aim is to find out the element. and you know that your element is present in the left half. So shift your search space there. How do you shift your search space there? You already know it. High equal to mid minus 1. Binary search, right? If it is not present in the left half, then you do what? You shift it on the other half, which is your right half. How do you do that? Again, it's the same thing. Low equal to mid plus 1. You shift it on the right half now. Okay. So this is what happens if your left half is sorted. Now, what if your left half is not sorted? If your left half is not sorted, then you check if your right half is sorted or not. I mean, if your left half is sorted, then your right half is already sorted. So then you check if the element is present in the right half or not. Okay. And then you shift your search space accordingly. Let's try to dry run this. Okay. So our array starts from here. We have 4, 5, 6, 7, 1, and 2. And we had already calculated mid. Okay, we had already calculated mid. So it's there with us. Okay. So it's very simple now. This is low. This is high. This is mid. Now tell me. My target is 0. It's better I keep it down below here. Good. Now you tell me, is 0 present in my left half? By putting in this condition. No, 0 is not present in my left half. What will I do? I will ignore this left half. Okay. And I will consider the right half. So my low, so according to my condition, low will be equal to mid plus 1. Yes. So how will my search space change? So my new low will be 0. Okay. So this will be my new low. So my mid was 7. I just shifted to 1 space right. So now my new array is 0, 1, and 2. Okay. My new array becomes 0, 1, and 2. Where this is my low. As you saw, like I shifted to low to here. So this is my low. My high is still at 2. I haven't changed it. And my mid now becomes this. Okay. I will again check that which part of my array is sorted. Okay. Is my left half sorted? So this is my mid. You check if 0, 1 is sorted or not. Yes, 0, 1 is sorted. I mean, 0, 1 is sorted, right? It's sorted in descending order. Great. Now I will check if 0 is present in that sorted array or not. Yes, 0 is present in the sorted array. How do I check that? By this condition. So this condition will hold true because 0 is equal to the target. So it will hold true. And so that means 0 is present in my left half. Okay, so then I will ignore my right half. I will shift my search space on the left. Okay, so my new array becomes 0, 1. Cool. Cool. So my low is remaining at low. My high became here. Okay. And you understood what I did here, right? I did this one, high equal to mid minus 1. Okay. So what I actually did here was high equal to mid minus 1. Okay. Now this is my low. This is my high. So my mid becomes, if you look at it that way, my mid becomes 0, 1, 2, 3, 4, and 5. 4 plus 5 by 2 is 4 plus 5 by 2 is 4. So this is my mid element 2. Now you check, is your left half sorted? Yes. Remember what was our condition? ARR of low was less than equal to ARR of mid. So now low and mid are both same. So of course this is sorted. If this is sorted, now I check if my 0 is present in this half or not. Yes, my 0 is present in this half. So I will shift my search space here. I will ignore this. My new search space becomes 0. And as soon as it becomes this, you understand that, you know, my high goes here. And now you understand that my answer, I've actually reached to my answer, and my index you already know. So 0, 1, 2, 3, 4. So my answer is 4 here. Okay, which was my answer here as well. Okay, so this is how the algorithm works. Okay, so essentially what we try to do in binary search is that we try to reduce our search space. Okay, according to our conditions, what we try to do is we try to reduce our search space. Okay, like you saw here. Okay, so my 0 was present on the right half. So you ignore the left half. So what is the benefit of that? You reduce your search space, so your array becomes smaller and smaller and smaller. I mean, your array literally does not become smaller, but your search space becomes smaller and smaller and smaller. And you make it smaller and smaller and smaller until you reach to a single element, or low or high, cross each other, right? So in the binary search, we have a condition like low is less than equal to high. We'll start to code that. So as soon as they cross each other, or the search space becomes as small as a single element, then you know that you have actually reached to your answer. Like here, the answer was index 4. Okay. So this is search in a rotated sorted array, and needless to say that the time complexity here, you already know, it is O of log n, because we applied binary search here. Okay. We applied binary search here. Okay. Great. Now, let's try to code this up. It's also very, very simple. Okay, how do I start with the binary search? First, I will need the size of my array. Okay. In C++ or Java, it's the same thing. In Java, we'll use array.size. In C++ also, it's very similar. We'll do arr.size. Okay. Cool. Now, in binary search, we have 2 pointers. You already know that the left pointer always remains at 0. The right pointer remains at the last index. What is the last index? N minus 1, if n is the size of my array, which I have already defined here. Okay. Now I will just start my binary search algorithm, which is, I'll just start a while loop. Until and unless the low and high pointers cross each other, this binary search algorithm will continue. And here you already know how to find out the mid, which is L plus high by 2. And here I need to check if at any point of time I have reached my target. So if any point of time my ARR of bit becomes equal to the target, means I've already reached my destination or my target. So in that case, I will simply return by index, the index of the element which we need to find. Like in case it was in the first example, the index of my 0, if we have reached to 0, I will simply return the index of my 0, which is 4. And that will be my answer also. But else, other than that, I will need to do what I just explained you here. I first check if my which half of my array is sorted. Okay. So I can even copy this if you want me to. Okay. So you check that if the left half is sorted or not. This is how you check if the left half is sorted or not. Okay. First of all, I am using ln high here, ln h here. So I'll just continue to use that. If the left half is sorted, then I need to check if my element is present in the left half or not. Okay, how do I check that? If ARR of low is less than equal to target. If the target is in between L and mid, that means my target is present in the left half. Okay. Once you know that the target is present in the left half, you just shift your search space accordingly. So high equal to bit minus 1. Else you already know it is low equal to mid plus 1. Cool. Now, what if your left half is not sorted? If your left half is not sorted, the right half has to be sorted. Why? Because that is the feature of a rotated sorted array. One half has to be sorted because the array was initially sorted, you rotated it. So after rotating it, one half is always sorted. That is one of the features of rotated sorted arrays, which you'll also see in a couple of other questions as well. But okay. So this means the right half is sorted. I'll again check if my element is present in the right half or not. How do I check that? I will simply check that if my element is present in between, if my element is present in between mid and high. If my element is present somewhere in between mid and high, that means my element is present in the right half, this half here. Okay. So I just need to check if ARR of mid is less than equal to target, and then target is less than equal to ARR of high. I'm representing high by H here. Okay, great. If my element is present in the right half, you shift your search space there, low equal to mid plus 1. Else high equal to mid max, opposite of that. Okay. Now, as soon as you find your element, you will return your answer. But what if your element is not found in the array? Like let's say I take target as 8 or something. 8 is not present in this array. What will you do here? In that case, after your after your execution stops of the binary search, that essentially means that our whole execution has ended, but we have not found out the index yet. So we'll just return -1. Okay. So we'll just first try to run this code and see if we have any errors or not. If we have errors, okay, we don't have any errors. This is getting accepted. Okay, so let's try to submit this and try to see if we have any errors or not. Okay, we don't have any errors. You see that we have a success. Okay, so yeah, this was the solution of search in a rotated sorted array. Now let me know if you guys have any questions or not. You guys have any questions? Okay, okay, sure. So I can move on to the next one. Okay, so the next one is also a pretty similar question. Pretty similar question in the sense that it also uses a rotated sorted array. Okay, so you already know the benefits of rotated sorted array from the first question itself. You have already seen all the benefits of rotated sorted array from the first question itself. So you can use that now. Now this question is very simple now. Okay. So what does the question say? The question says that the array is sorted in the ascending order, but then again, it has been rotated exactly the same way as the previous question, rotated sorted array. I simply need to find out what is the minimum element of this array. So, okay, so it's a very, very simple question. You just have a rotated sorted array and you simply need to find out the minimum element. Okay, so my job is to find the minimum element. That is exactly what the question says, nothing more. Nothing more. Okay. So one more point is that, okay, anybody can find out the minimum element in O of n. This is a O of log n time you need to solve it. Okay, so that is one extra note that we see in the question. Okay. So how do I solve this? Again, this would be very similar to the question which we solved just now. Okay, it will again be a modified binary search, and we will use the same concept of my rotated sorted array, where you know that if you divide this array across a pivot, if you divide this array across a pivot, but the left half, if it is sorted, then the right half is not sorted. And if the right half is sorted, left half is not sorted. So one half of the array is always sorted. That is the benefit, that is the feature of rotated sorted array. So we'll use that same thing here as well. Okay, so 0, 1, 2, 3, 4, 5, 6. So this is our mid element here. And you see that this half is sorted. This half is not sorted. Okay. Okay, what do I have to find out? I need to find out the minimum element. Okay. Again, I need to do something very, very similar to the thing what I did in the last question itself. I need to check which half of my array is sorted. Okay. I need to check which half of my array is sorted. Same thing as my last question, exactly the same thing. Just find out which half of my array is sorted. And you already know how to check that by this one. Okay, so this means that the left half of your array is sorted. This is exactly what we will use here as well. You check if the left half is sorted or not. If the left half is sorted, then you can easily find out what is the minimum element in your left half. Okay, how? If the left half is sorted, take this example, 4, 5, 6, 7. What is the, this is, you know that this is sorted, 4, 5, 6, 7 is sorted. So what is the minimum element in this 4, 5, 6, 7? What is the minimum element in this 4, 5, 6, 7? Obviously 4, because the first element of a sorted array is always the minimum. If an element is sorted in, like if an array is sorted in the increasing order, the first element will always be the minimum, right? So that is the advantage of sorting. So you already know that your low pointer, ARR of low pointer, will be your minimum element if the left half is sorted. Okay. But if the right half is sorted, what if the right half is sorted? Then how are you going to get that? If the right half is sorted, okay, we will get there when we actually solve this particular question. Okay, so let's start solving this particular question. If the right half is sorted, then ARR of mid becomes your minimum element. How? I'm showing that to you once I start dry running this, right? Okay, let's try to solve this question. Let's try to dry run this question. Okay, very easy. So what I will simply do is I'll just start the binary search algorithm. So here is the low pointer, you know it. Here is the high pointer, you know it. And this is my mid. We know it. Now I need to check if my left half is sorted or not. Yes, my left half is sorted. So what I will do is I'll just take the minimum element, which is 4 here, and then I will shift the search space to the opposite. Why? Because I have already collected the minimum element from this left half. But there are elements, there can be elements which can even be smaller than my minimum element present in this half. Once I have picked up the minimum element from my left half, I already know that the other elements can never be my minimum element because I've already picked up my minimum element. So then what I can do is I can just pick up my minimum element and shift my search space over here. In this half, this will be my new search space. Why? Because 4 is the minimum element in my left half. But there is a possibility that there are even smaller numbers than 4 which are present in my right half. Is there a possibility? Yes, it is. You can see here, like 0 is less than 4 here, but in the left half, among the left half, 4 is my minimum element. But there are elements which are even less than 4, which is present in the right half. So the idea is, the idea to solve this question is, you check first of all, you check which half of my array is sorted. Whichever half of my array is sorted, pick up the minimum element from that half. Pick up the minimum element from that half. Clear? I just check which half is sorted, pick up the minimum element from that half. Clear up till now? After that, what will I do? I'll just do one more step and then we are done. I will simply shift my search space to the opposite half. Okay, I will shift my search space to the opposite half. Okay, this is my opposite half. Why? Because it is a great possibility that in the opposite half, I have elements which are even smaller than the current minimum element in my half. Okay, so if you want me to dry run this, how will this occur is, okay, you saw that the left half is sorted and you see the minimum element is 4. So you take up a variable here called mini and this stores 4. And after it stores 4, your new search space is 0, 1, 2. So 0, 1, and 2 is your new search space after you have picked up the minimum element from the other half. Okay. Now we will do the exact same thing again. So my high is still here because I haven't changed high. So my high still remains here. My low remains here. And my mid is this. Cool. Now what I need to do is same thing again. I check if my left half is sorted or not. Yes, 0, 1 is sorted. If 0, 1 is my sorted, then you know the minimum element of a sorted array is its first element. So now you see mini is 0, right? So what I will do is I will simply do mini equal to minimum of the previous mini which I had, comma, the current mini which I have, which is 0. So if you do here, minimum of 4, 0 is 0. So the currently 0 will be stored in mini. Okay. And once 0 is stored in this mini, then you shift your search space to the opposite half. Okay. So I will ignore 0. I will ignore 1. I will shift it to the opposite half. How will I do that? You know it. Low is equal to mid plus 1. Cool. So my new search space becomes 2. My new search space becomes 2. And now again, I will do the same thing. I will divide this into 2 halves. But again, we like if you look at it, I don't think we will even divide it into two halves, because I guess high and low are at the same point, right? Because this was high, and when we did low equal to mid plus 1, this is also low. So low and high have touched each other, so that's good. But again, we will do mid. Okay, so my mid will be this on only. If you do mid equal to low plus high by 2, and low and high are both same, so this will also be your mid as well. Okay, so this will also be your mid as well. So once you see that this is your mid, we'll again check if my left half is sorted or not. My left half is sorted because it's a single element, it is sorted. So if this is sorted, I need to do minimum of the minimum element which is found here. So which is mini equal to min of, the previous minimum is 0, the current minimum is 2. So it is 0. So the minimum element which is found now is 0. It's still 0. And once it is found, I will shift it to the opposite half. When I shift it to the opposite half, you see what happens. My low comes here. And once my low comes here, my high is still here at 2, but my low has come here. So that means low has crossed high. And by the definition of binary search, whenever low crosses high, then you know we need to stop our algorithm as soon as possible, because we are breaking the rule of binary search. Low pointer always has to be on the right, always has to be on the left, or always has to be on the right. They can also be equal, but they should never cross each other. Okay, so L has crossed high, so our algorithm stops. And what is our answer? Our answer is 0. And indeed, the minimum element is 0 here. Okay, so that is how we are going to solve it. It's very similar to the previous question. So let's come here and let's try to code this up. This will be very similar to the previous question. Okay. So nums.size in Java also they dot size, but apart from this, the whole code remains the same. So in Java and C++, both will have the same code after this line. So okay, low remains at 0, R remains at n-1, first index, last index. Cool. Starting our binary search, L less than equal to R. We'll find out the mid element. You know it, it's L plus R by 2. L plus R by 2. Cool. Now I need to check if left half is sorted or not. How do I check that? If my ARR of low is less than ARR of, okay, I am using nums here. So in the example, I was taking ARR. So I'll just take nums here. If nums of L is less than nums of R, not nums of R, nums of mid, that means my left half is sorted. Okay, it can also be equal. So don't forget to give a equal to here. Okay, so left half is sorted. And now what I need to do is I need to pick up the minimum element from this half and shift to the other half. So I'll just pick up the minimum element from this half. It is min equal to many comma. What is the minimum element from the, what is the minimum element in a sorted array? The first element, if the array is sorted in the ascending order. So what is the first element in this array? Nums of L. Low pointer, right? Then I shift it to the right half. So low equal to mid plus 1. Else, my minimum element will be my mid element itself, because the last element here is my ascending order. I mean, this is a normal ascending order. You know it, that if this is this has to be my minimum element, because you go on the right, your elements will only increase because the array is sorted in the ascending order. So this will be nums of mid. Cool. I will shift my search space to the opposite half, which is in this case left half. Done. We are done. What will be our answer? Our answer is stored in mini. Now I haven't used any variable called mini here, so let's also define that. Int mini will be equal to, we can take 100,000, but it's safe to assume here int max. Whenever we find out the minimum element, you already, I guess, know that whenever we find out the minimum element, we always initialize it with the maximum possible value. Whenever we want to find out the maximum element, we initialize it with the minimum possible value. Okay. Okay. Let's try to run this code and see if we have any errors or not. Okay, we have an error. What is that error? High is not found, undeclared high. Okay. Okay, we are using R here. We should use H here. Okay, let's run the code. Yeah, so I see a question in the chat. I see a quick question in the chat. It says, can't we solve the first question just by linear search? Yes, you can solve the first question by linear search, but the time complexity will be more. Like the time complexity of linear search is O of n. But you needed to solve that question in O of log n. So that is why you needed to use binary search there. And also after you after you cross this, when you come to like when you start with the interviews, after you tell that solution the solution which you are telling by normal linear search, the interviewer will ask you to even optimize this. Or also, in the paper, right, in the NQT paper, if the time constraints is a bit tight, then linear search won't work because it will give you time limit exceeded because your solution is not optimal. So depending on the time constraints, you can decide between uh, using linear search or you using binary search. But nonetheless, you have to ultimately you need to optimize the solution, and ultimately you will need to come to binary search. Yes, if the time constraints are not that strict, you might use linear search as well for quick solution. Yeah. Okay. Meanwhile, our solution is accepted. It's a success here. Okay. So yeah, it's a success here. This is also O of log n. So yeah, I hope you understood this question as well. Same thing. Check if the left half is sorted or not. If it is, pick up the minimum element, shift the search space to the opposite. If you're right, else if the right half is sorted, pick up the minimum element, shift the search space to the opposite. Okay, because in the other search space, there is a possibility that we have elements which are even less than the current minimum element which we have. That is the whole concept of this video, of this question. Okay. All right. So this is accepted. We are good to go. Okay, I have one more binary search question as well, but this is a similar question, but I want you guys to solve this question first. This is a question on stacks and queues. Okay, so I'm coming down to stacks and queues. Okay. Okay, I'm giving you the hints that this will be solved by stacks and queues, but okay, in a real exam, you won't get that. You actually need to decide also that which data structure you're going to use. You have to decide that once you read the question. But okay, let's try to read the question and let's try to understand what the question is saying. Okay. What is the question saying? Okay. So we are given an array asteroids of integers which represents the asteroids in a row. For each asteroid, the absolute value represents its size, sign represents its direction. Okay. Okay. So find out the state of asteroids after all collisions. If two asteroids meet, the smaller one will explode. If both are same size, both will explode. Okay. If you are getting a bit, if you're like if this is getting a bit tricky, let me try to explain this with the help of a simple example. The examples here are pretty simple. I'll take an example of my own. Okay, let's say I have 4, 5, 6, 7. I'm just taking a random example. Okay, I have -5 here, and let's say I have, okay, let's put this 7 here. Let's say I have something like this. Okay. I will need a smaller element here. Okay. So let's say we have an array like this. Okay. It's very, very simple. Listen to me. This is like, yeah, if you listen to me, this question, like, it's very simple to understand. Okay. So what this means is every positive integer, right? I'm making the question simple for you. Every positive integer means the asteroid is going in this direction. So if this is your asteroid, Your asteroid is actually going in this direction if for every positive integer. Okay. For every negative integer, your asteroid would be going in the opposite direction. So it's better I do it something like this. Okay, so that is the simple meaning. So if we look at this array, every positive integer is going in this direction, in left to right. Every negative integer is going from right to left. Cool. Now, according to the question, whichever is whichever is greater, okay, a higher value will destroy the lower value. Okay, so if two asteroids collide, the higher value will destroy the lower value. This is point number one. Okay. Well, point number two is if two asteroids of same strength, okay, if two asteroids of same strength collide, both get destroyed. So this is all the question says. Okay. A higher value will destroy the lower value if two asteroids collide. Otherwise, if both the asteroids are of the same strength, both get destroyed. Okay, so if you look at this, if you look at this, the way this will occur. So what it will here happen is, if you look at this, so two, we have 2 here, right? And we have -5 here. So -5 will actually destroy the one with 2 because -5 has a lower value. Okay, so 2 is destroyed. Okay, 2 is destroyed. What is next in my what is next in my array? The next in my array is 5. So if we have a 5 here and if you have a -5 here, both are of the same strength. So both get destroyed. So this will get destroyed, this will get destroyed. So in the array, this will get destroyed, this will also get destroyed. Okay. After that, we have another -5 here and we have 7 here. So you have 7 here and you have -5 here, which is in the opposite direction. In this case, you know that the higher value will prevail. So -5 will get destroyed. Okay, what we'll have is 4. So your final array will be, your final array after all the destructions will be 4, 7. This would be your final array. Okay, so this is exactly what the question states. Every positive and every negative asteroid will have to collide each other at some point. So you start from the center, 2 and -5. -5 has a higher value, so 2 will get destroyed. Done. After that in the row we have 5. So 5 and -5 both are same value, both get destroyed. Then we have -5 and 7. -5 get destroyed because 7 has a higher value. Now here both have positive value, so both are traveling in the same direction. So they can never collide with each other because they are not traveling in the opposite direction, they're traveling in the same direction. Okay, so your final answer will be 4, 7 in this particular array. Okay, we don't have this example here, but yeah, if you want to take this particular example, then you also know that if you want to take this particular example, then you know that 10 and -5 will collide, so -5 will get destroyed. So your final answer will be 5 and 10 because 5 and 10 are going in the same direction, so they can never collide. So that will be an answer. Okay, here you see 8 and -8 both will collide, so we don't have any asteroids, so this will be empty. Both asteroids have been destroyed. In this case, you see we have 2 and -5 at the beginning. So 2 will get destroyed because -5 is higher, and then -5 will get destroyed because among 10 and -5, 10 is higher. So answer will be 10. Okay, so this is what the question says. Okay, this is exactly what the question says. Okay. Now, how do I solve this? I will take this as an example because this is a better example than all the lead code examples we have here. Okay, this is very easy. It can be solved using stacks. Okay. Do you have any questions? Yeah. You're asking if both half is sorted, or you are asking about the rotated sorted array, right? Yeah, one half is sorted, the other half is not sorted. Whenever you have a rotated sorted array across a but across your mid element, the property of a rotated sorted array is if the left half is sorted, the right half is not. If the right half is sorted, the left half is not. That is a property of a rotated sorted array. Okay, coming to the previous question, but okay, let's try to solve this question with the help of stacks. I mean, you kind of get a hint that this question will be solved with stacks, especially when I explain this, we were actually colliding from the middle. So that means from the middle, if two asteroids collide, the lower strength asteroid will just destroy itself. Okay, if they are same, both will get destroyed. Okay, here you see 7 has a higher strength, so 5 has got destroyed. Okay, so what you do is very simple here. Okay, yeah, what you do is very simple here. You just take a stack. Okay, let me just do this. You just take a stack here. Cool. You start putting elements into your stack. We start putting asteroids into your stack. First, we have 4. Good. And you know the concept of stack, right? Very important for exams, like LIFO concept. I hope all of you guys know last in, first out. Okay. Great. So first, the 4 is entered into the stack. Then we have 7. I'm entering it. Then we have 5. Then we have 2. Okay. Then we have -5. So the concept here is if the element is positive, if positive, enter into stack. For now, if the element is positive, enter into stack. There is also a possibility where you might need to enter negative elements into your stack. We'll come to that. But first, if it is all are positive, just one by one start putting it into the stack. Cool. Now I get -5. This is my first negative element. Now what I need to do is I just need to check if, okay, this is -5. So we take, whenever we compare the strengths of both the asteroids, I will just need to take the absolute value, right? Because like if you look at this, -5 has a higher strength. Okay, but 2 is more than -5. That won't work. So you take the absolute value. This is 5, this is 2. So 5 has a higher strength. So whenever you have a negative value, just take its absolute value. Okay. So it's very simple. What I need to simply do is just take the absolute value of your asteroids I, right? The name of the array is asteroids. I know that asteroids of I is negative. I know that. That's why I have not put it into my stack. I have not put my -5 into my stack yet. I know it's negative. So if the absolute value of asteroids I, if the absolute value of asteroids I is more than stack's top element, then you know what will happen. Then whatever is inside my stack, it will get destroyed because that has a lower strength. My stack top is less than this, which means the stack top has a lower strength. So essentially, this will get destroyed. So instead of a if condition, this will continuously happen. So I can write, instead of a if, I will write a while loop here. And until and unless this happens, I will continuously start to destroy elements from my stack. How do you destroy elements from your stack? Simply pop out the elements. So just do s.pop. Until and unless, you find out that, this guy, this asteroid guy, the negative guy is stronger than the positive guys, you continuously have to destroy all of these positive guys in the stack until and unless you find someone who is even stronger than this guy here. Okay, so you just run a while loop, and until and unless you find out that the stack elements are weak, they all will get destroyed. Okay, so you just, until and unless that happens, you just pop it out, keep popping out from the stack, keep popping out from the stack. Okay. Okay. There was also one case, you remember, where both had the same values. So if both have the same values, both will get destroyed. So that condition will also be need to put. Okay, but yeah, first let's complete the dry run. So I had put 4, 5, 7, 2. We had -5. -5 is more than 2. Absolute value of -5 is 5. So 5 is more than 2. So 2 has got destroyed. Cool. After this, I see 5 and -5 both have the same values. If both have the same values, both will get destroyed. So you destroy it from here, destroy it from here too. Destroy. How do you destroy it from here? You just continue. Okay. In the map, how do you destroy? You just ignore it. How do you ignore? Continue. Continue. Okay, just we have a continue. Just continue. Ignore it. Okay, after that we have 7. Now tell me the next element which I have is -5 as well. Okay, and the top of the stack right now is 7. Is which one is greater? 7 is greater. So you destroy my -5 and we are done. Why are we done? Because all the elements are positive. So that means my answer is in the stack 7 and 4. Okay, so it is 7 and 4. So it is 4 and 7. So my final answer is 4, 4, 7 because those are the two elements which are remaining in the stack. Okay, and that was my answer as well. Okay, if you see here, 4, 7 was my answer after all kinds of destructions between all kinds of collisions between asteroids. Okay, so okay, this is all cool. But one thing I need to mention here, which I don't need to forget here, is that there can also be a case. There can also be a case where I need to enter negative element into my stack. Okay, if somehow I have a negative element in my stack, then and the array element which I have here is some -6, then these two cannot collide with each other because they are all traveling in the same direction. So they cannot be, both are negative, right? So they're all traveling from right to left. They cannot collide. In this case, you need to put this element into the stack. So this one if condition needs to be there to handle this particular case. But other than that, this question is very simple. Let's start to code this up. Okay, so we'll take a stack first of all. Okay, we'll just take a stack first of all. Okay, this has to be done slowly. Stack int s. Okay, I need to return a vector here. Okay, vector means a array list in Java or even a array in Java. If you go to the Java here, it is array. So it's even more simple to do in Java. It's a normal array. Okay. Okay, so for C++, I'll just take a vector of int of answer. This answer will store my final answer, which I will return. So I can even do that now, return answer. Okay, in between, I will calculate my answer. Okay. Okay, here I will start coding my solution. Okay. What did I do? So I will just run my loop, and for all the positive values, I will start putting it into my stack. Put. So if my asteroids of I, if it is positive, then I will start pushing it into my stack. S.push, it has to be asteroids of I. Cool. Now coming to the else part, it means now asteroids of I is negative. If asteroids of I is negative, you remember what did we do? We had a while loop here, and until and unless this element is bigger, all stack elements have to be popped out one by one because this has a higher strength. Okay. So the way of doing it is, okay, first we check the stack cannot be empty, right? Because that is one more case, where I personally have faced issues there when I don't write stack is not empty. And if the stack is empty, you cannot do it also. Like you cannot pop from an empty stack. So, okay. So stack cannot be empty. And my absolute value of asteroids of I, because I know that now asteroids of I is negative. If it has come to my else, now asteroids of I is negative. So absolute value of asteroids of I, if it is stronger than my top element, then I'm sorry, but my top elements have to be deleted out from my stack, popped out from my stack. But one thing you need to make sure in this case is that stack element has to be positive in the first place, because if stack element is negative, you remember this case, if stack element was negative, I can even enter a negative element into my stack. Okay, but so in this case, stack element has to be positive first of all, right? So it has to be greater than 0. Okay, don't forget, like we are already putting positive elements into our stack. Okay, so this has to be positive. Okay, this should do, but now is the case where both are same, both will get destroyed. So again, I just need a if condition, stack is not empty, and I can just copy this maybe. So absolute value of asteroids of I is equal to my stack.top. Okay, so yeah, in this case I will pop out as well, right? In this case I will pop out as well. Okay, and in that case obviously asteroids of I will be ignored. But other than that, we have one more case. let's put this properly. Yeah, the one more case was this case which I was telling you. If my stack element has a negative element, then I am able to put a negative element because these two won't collide. Okay, so don't forget to put this up. Okay, so in case, or we have one more case, or if my stack is empty, if my stack is empty, then I can put my -6 here, right? Then we don't have any harm in putting a negative element if my stack is empty. So if my stack is empty, let's say, or the stack element is itself negative, stack element is itself negative, which means s dot top is less than 0. In that case, I can push asteroids away. Now you might have a question that from the beginning, I am only inserting positive elements into my stack. How come we have a negative element here? You can have a negative element here. Why? Because of this condition. If the stack can be empty at some point, if this, all the asteroids have collided with each other, then what? Stack has become empty. If stack has become empty, then you cannot ignore a negative element. You need to put it. And as soon as you put a negative element into your stack, now your stack has a negative element, and then this condition will play. This particular condition will play. The stack element has to be positive. Then if it is a negative, you can further put negative values. So this is the thing. If your stack is empty, then you have to put negative elements. Okay. So this is one catch which I missed in the first case, but now I know. Okay. So that was the only condition that, if the stack is empty, don't forget to put your asteroid, because that is a valid asteroid. It can harm somebody else later on. Okay. Okay. But what I need to return is a vector int answer. Okay. So my stack contains my answer, but I need it in a vector. So what I'll do is I will simply pop elements from my stack and put it in my vector. So I'll simply pop off all the elements from my stack and put it into my vectors, just replacing my elements from stack into my vector. So answer dot push back. What do I need to do is s dot top. And you do s dot pop. So I'm simply shifting all my elements from my stack to my vector. Why? Because I need to return a vector here. Okay. Okay, but I guess this will be in the opposite direction. If I run my code, it will give me wrong answer, right? Because it is in the opposite way. Yeah, you look, expected is 510. I'm getting 10.5. So I can reverse my answer, right? I can simply reverse my answer. Reverse answer dot begin, answer dot end. Okay, now if I run this, yeah, now it's getting accepted. Okay, so if I submit this, and we have a success here. Okay, so yeah, that was our solution. And time complexity will be around O of n, because this while loop. You might say that a loop is present inside another loop, but again, this loop is not running n times. It's running much less than n times. So this almost you can consider it as a constant. Okay, so this overall you get the time complexity for this loop only. It's around O of n. And space complexity, the extra space complexity is you are using a stack, so it's space complexity is O of n as well. Okay. Yeah. All right. So yeah. So that was it, and let's meet in the next live class. I hope you have understood. If you have any questions, do put it in the YouTube comments below. All right. Thank you, everyone.